Today we will be studying complex numbers for linear circuit analysis. Uh, Complex numbers can be represented in two different forms: uh, rectangular and polar form. In rectangular form, they can be represented as C is equal to x plus minus jy, where x is the real part, y is imaginary, and j is also called iota. This is -1 square root. In linear circuit analysis, we use j instead of I because we use I to represent AC currents. Whereas as a polar form, this can be represented as C is equal to R, triangle of plus minus theta, where they are interconvertible. We can convert the rectangular form of the complex number into polar and vice versa. In order to convert from rectangular to polar, we can work like R is equal to x square plus y square, the square of real part plus the square of imaginary part and the square root, and theta can be calculated as a tan, inverse tan of the ratio of imaginary part to the real part. And we can go back from polar to rectangular by putting x is equal to r cos theta and y is equal to r sin theta. In order to having simple arithmetic with the complex numbers, we can write the sum of two complex numbers c1 plus c2 as x1 plus jy1 plus x2 plus jy2, where x1 plus jy1 is c1 and x2 plus jy2 is complex number c2, both in their rectangular form. You can just add x1 with x2 and the imaginary parts are added into imaginary plus jy1 plus y2, right? Just so adding two complex numbers is easy if they are in their rectangular form. Similarly, subtraction is also easy if they are represented in the rectangular form. So we just have to subtract the real part from the real and imaginary from the imaginary. So it's x1 minus x2 plus j y1 minus y2. So, but in order to multiply and divide two complex numbers c1 and c2, for example, I want to multiply z1 and Z2 together. So this becomes easy if they are in the polar forms. Right? The magnitudes are multiplied together. R1 is multiplied with R2 and thetas are added together. So this is simple. Similarly, division is also easy. Two complex numbers C1 and C2 can be divided like this. R1 at an angle of theta 1 divided by R2 at an angle of theta 2. So R1 divided by R2 at an angle of theta 1 minus theta 2. The magnitudes are divided and the angles are subtracted. There are some other important properties of complex numbers we can say. For example, what is 1 over j? 1 over j. If you multiply it with j and divide it with j, this becomes j over j square. Since we already know that j is square root of a minus 1, therefore this is j divided by j square is minus 1, so we can write it as minus j. So 1 over j can be written as minus j. So this is another important property of complex numbers. In some situations in circuit analysis we have to rationalize the denominator. For example, if we have to work with this quantity 1 over 1 plus j1, the complex number is in the denominator, so we can get rid of this complex quantity in the denominator by multiplying the fraction with its complex conjugate. The complex conjugate of 1 plus j1 is 1 minus j1, so this becomes 1 minus j1 over, this is 1 plus j1 but here 1 minus j1, so this is actually a plus b multiplied by a minus b. From the elementary school we know this is equal to a square minus b square. So this becomes 1 minus 1 square minus j1 square. So this becomes 1 minus j1 over 1 minus j square. J square is minus 1, so this is 1 minus j1 over 1 minus 1. This becomes 1 minus j1 over 2. So we get rid of the complex quantity from the denominator. This is the simple arithmetic that we need to know in order to apply complex numbers to AC circuit analysis. Hope this arithmetic calculations will be useful for the problems involving complex AC quantities in the course linear circuit analysis. Thank you very much.